Hey guys, Rich, Mr. Thrive and Survive. I did a pretty long video yesterday, but for some reason my computer does not want to cooperate with videos that are long. Probably a lot of you are glad I don't have a long video up there, so I'm going to make this really short, leave out a lot of stuff. I had density altitude charts, pressure altitude charts. I was going to show you how looking over a long distance is nothing for refraction purposes, density purposes. You know, you have people that think they know what they don't know. This has been my thing, guys. From the age of 5 or 6, I've been into weather. I'm 56 years old. I did this as my profession. I understand this. Let's look at this glass of water. Less dense air, more dense water. The greater density water makes the spin bend which way? Down. More density makes it bend down. Now, I had all kind of things explaining this. I'm just going to try to make it as simple as possible. You're going to think I'm crazy, but moist air or air that's got rain in it is less dense than dry air. Look it up if you don't believe that. Please, look it up. So, even if you are looking through rain, what that's going to do is that's going to make you looking into a less dense. If you have rain between you and the mountain, chances are you won't see the mountain if it's far away, so you even won't be able to tell if the earth is flat. You're looking through if rain is in front of you, between you and the mountain, because people say, well, you don't understand, Rich, looking through layers of rain and different things like that, or moisture and things like that. Yes, I do understand. The more moisture, the more you are making it less dense. All right? So if you're looking through if you have a whole bunch of moisture, it makes it less dense, right? Less dense does bend up, but you're not going to see the mountain in that situation. When you actually can see, when you can stand on, like we saw the 45 to 60 mile pictures from the shores of Lake Michigan, looking at Chicago, there's no rain in there. There's no fog. If there is, you can't see Chicago. So you're getting a more dense atmosphere. More dense is warmer, drier, higher barometric pressure, a lower dew point temperature. All these things come in. Dew point temperature puts all the factors together. This is very important. I'm going to show you this in one swoop here, that when you look at something distant, okay, you cannot possibly look far enough and have that much of a difference where you're going to see any refraction. And I'll prove this to you in this video. I will prove it to you. It can be proven if you have a telescope. So, let's watch. Now we're going to take a look at two different things here, two different weather observations taken 1 minute apart. 11:54 Eastern for Crofton, Maryland. That's between Baltimore and Washington, D.C. And 11:53 p.m. Eastern Daylight Time for Hagerstown, Maryland. Hagerstown, Maryland is in a high plain type area, gently rolling hills, where you have very low mountain ranges just west of there. So if the earth was flat, you could see from Crofton, Maryland, 70 miles away to Harrisburg. They're 70.7 miles away. 70.7 miles away. Don't believe me? Look it up. You can look up any of this stuff. And that is as the crow flies, not driving. Driving distance is about 86 miles. However, we have eastern deciduous forests on the east coast of the United States in Maryland. You cannot see more than a block in Crofton, Maryland West because there's trees everywhere. So, but what I want to point out is if you were looking from Hagerstown to Crofton or Crofton to Hagerstown, either way, it's 70 miles distance. Remember, most of the time we're talking 45 to 60 miles at most when we're talking about doing flat earth calculations. Most of it is much, much, much closer than that, isn't it? I'm going to show you something here. Dew point temperature right here, 42 degrees Fahrenheit. This takes into account all the things that are necessary for refraction. All of the things necessary are included in the dew point. Why? Because the dew point is a calculation of many factors. The dew point will change with a change in barometric pressure, your relative humidity, wet bulb temperature, dry bulb temperature, density, altitude. I mean, all these things go into the dew point. So if you have big differences in dew point temperature, that's when you can have big differences in refraction. Why? Because dew point temperature is where dew will start to condense. The higher the dew point temperature, the more moisture there is in the air. The lower the dew point temperature, the less the moisture is in the air. So 70 miles away in weather, guys, unless you have a strong front in between the two cities that are 70 miles apart, let's say you have a cold front in between the two cities, first of all, you're not going to see, even if it was flat as hell on a very clear day, 70 miles when you have a strong cold front, because you're going to have rain. And that's going to make the air less dense that you're looking through. That is when you could have refraction. On the clear, dry days, that's when it should, if anything, bend downwards. Dry makes you see, gives you the appearance of less, not more. We saw that with the glass. All right, dew point temperature at this time, remember they're only a minute apart, 42 degrees Fahrenheit. 41 degrees Fahrenheit. It's 1 degree Fahrenheit. For you, those of you over in Europe, that's about 0.6 degrees, 0.6 degrees Celsius. Look at these vapor pressures. I'm not going to go into them here. There's like 25 or 15 1,000ths of an inch of mercury different. There's virtually no difference. Look at the difference. Air density. Okay, with water vapor, 99%. Air density with water vapor, 99%. We have 99% without water vapor, which is not true because every place has water vapor, would be 99% here. It would be 100% here. So the air density is virtually, they both have water in the air, obviously. Nobody has zero water in the air. They're both 99%. What does this say? The density in Hagerstown, Maryland, 70 miles to the west, is the exact same density of air of Crofton, Maryland, 70 miles to the east. It's actually to the southeast, to be exact. You're looking 70 miles, and there is absolutely, you pick up all the little towns in between that have weather stations. There will be no difference in the air density, in the water vapor in it. It just doesn't happen unless you have an extreme weather front. And in that case, you won't be able to see a far distance. In fact, the most extreme would be a warm front. And that's when you have low stratus and fog. That's when you can get those inversions that they claimed happen in Chicago. That's when those inversions are lifted like they showed. But what they didn't tell people was it was upside down, right? Yes. Of course, they made it flip upside down and then flip up again. But that would not happen 40 miles away. That could only happen when you have an extreme amount of difference in the density, such as fog or what's called, if you're familiar with the term clear air turbulence, it's where planes have turbulence where there's no clouds. That is because they have there's near 100% humidity in the air, but for whatever reason, or even at 100% humidity, for whatever reason, a cloud has not formed. Maybe there's no cooling process. Maybe there is no hydroscopic nuclei in the air. Something is not presenting the cloud, but the aircraft still knows it because when it hits dense air, what does it do? It drops. That's when you get turbulence. Have you noticed? You go through a cloud, boom. The cabin feels like it drops. It's because when it hits the cloud, okay, it's in less dense air. So the engines have a harder time pulling enough air through because it's less dense to keep it at the same altitude. Guys, this is my specialty. This is my thing. 70 miles apart. Got it? All right, let's go on. Now, let's go back to this real quick. Imagine it's a clear day because it's the only time you're going to see a mountain 70 miles apart. You're in Crofton, Maryland here. This is Hagerstown. It's more like hills, not mountains there. There's about, 500 or 600 feet difference between the altitudes of the two. So you're even looking up in the atmosphere through different layers. What was the difference in the dew point? What was the difference in the barometric pressure? Go back and look at those numbers. Minuscule. It's not enough. It wouldn't be enough if you had a laser pointer to see a 1/100th of an inch of refraction. And yet people want to throw, the refractive variant today is 22 feet. BS. Want the proof in the pudding? Here's the proof. Here's the proof. When you're looking from the surface, please get let me show a chart here. This is called a density altitude chart. That is the density of the air at particular altitudes. See the lines, how they slope up with altitude? This is your standard atmospheric pressure. This is where it normally is. This is the difference, okay? Well, this is the pressure altitude here. Let me show you that this goes into the density altitude, as you can see right here. This line going this way is the density altitude. Here's your figures over here at the 15,000 feet level, 10,000 feet, whatever. So you're going to have more refractive ability looking up than you are looking this way. Why? Because you're looking at a lot more than 70 miles in most cases. All right, you're looking all the way up to the stratosphere. Top of the atmosphere into the stratosphere. So you're going from a very dense surface all the way up to where there is no atmosphere when you're looking through a telescope looking at stars or whatever, correct? Absolutely. You're looking through much more telescope going up than when you do going this way. Now, let me explain a few things very quickly in case you didn't know it. You can get a telescope. You can put it on what's called an equatorial mount. You can put a drive on here and connect it to a computer that will drive this thing. You turn it on, it will recognize its latitude and longitude where the telescope is placed. You say, okay, I want to look at the moon. So it syncs up and it learns what your latitude, longitude, and your local time, and it pulls in the astronomical data that was written into this thing months, years, maybe even a decade earlier now. So this is how long this technology has been around. You can get drives from 10 years ago, 20 years ago, that still have data in it for now, that tell you when the sunrise will be, when the moon rise, when the stars, the planets, where they are in the sky. You can say, okay, show me Jupiter. This thing will say, all right, your latitude is 72.4 by 43.6, whatever, and your local time is this, and Jupiter should be right here right now, and the telescope will swing over and follow it the rest of the night. In fact, it'll follow it from the time it rises, gets overhead, and falls. So you're going to go through all different kind of conditions. When it's near the horizon, it's going to be looking at all the density this way of your atmosphere, and when it rises, it's going to be going through even more. You're going to be looking at even more. Okay? Now, what factors do we have? You could have clouds, you could have clear air turbulence where there's more. You're going to have a lot of areas of more to less dense, even with no clouds. So that will change if it was going from clear to water. You would think it would be enough change in refraction so that the telescope wouldn't follow it, right? The telescope doesn't actually see it. It doesn't say, oh, there's Jupiter. I got it in the center. I'm going to track it now. No, no, no. It's all by the computer. And guess what, guys? No matter what your atmospheric conditions are, it's not enough to keep it from being in the center of your telescope. It might move it, if you have really drastic differences between the surface and up high, you might get maybe, I don't know, maybe a quarter of an inch, what looks like a quarter of an inch movement from dead center in your telescope. Maybe, and you're looking at objects 250,000 to supposedly million miles away, and you're looking through all these different layers. You have clouds go by. When you look up at the sky, many people have seen this. You see the moon. You'll have sometimes puffy clouds go by, but you can still see the moon behind it. And you'll have high stratus clouds or high cirrus clouds move in front of the moon and things like that. It doesn't change the moon's position. It doesn't change the moon's position. It might make it brighter or less bright, but it doesn't change the moon's position. And you're changing drastically the amount of moisture you are looking through this whole layer of atmosphere when clouds go over it and not. Cirrus clouds you can see through. It doesn't change the position of the moon any. So you're going to tell me there's enough moisture looking east, west, north, south at an object on the horizon so that you have to calculate what refraction is? Come on, guys. It's bunk. This is proof. This telescope never fails. And it would fail. It might say, okay, if it's moist in the atmosphere, you might have to calculate, plus or minus whatever for refraction. You never have to do that. If it'll follow whatever you put in there, it'll follow it from the time it rises, goes overhead, and sets. It just will, guys. No errors. Years in advance programmed. And all this talk about the Earth shifting with every time there's a big earthquake. No, that's all bunk. We'll get into that another time. One last thing I want to cover because I saw it in the comments. Somebody was like, oops, you can't explain why you can see the sun at 270 degrees or 090 degrees on the equinox dates. Everybody on the Earth supposedly sees the sunrise at 090 degrees. I don't think that's true anymore. I think there's a couple degrees variation. I think we proved that now over the years. Doesn't matter. It is close. But here's the deal, guys. You can't explain it on a ball either. Oops. You cannot explain it on a ball either. There's no way you can have someone in North America, or let's say up near the North Pole, and someone down near the South Pole, and someone at the equator, and in between both the North and the South, all see the sun and the sunrise at 090 degrees on the equinox dates. It just doesn't work on either model. It does work, and it is in itself, this is the most underrated aspect of knowing that science is lying to us. And you can prove it yourself. Under certain conditions, if you're lucky, you can prove that science is lying to you. If you ever observe something called a rainbow, you can prove that science is lying. Because a rainbow, as science will tell you and has proven, requires 2 reflectors. If there's moisture between you and the rainbow, that's one reflector. What's the other? Between you and the sun. So we do not see the sun directly. That's what explains why everybody sees it at the same. I've got videos on this. I don't have time to go into it here. But that's why everybody sees the sun from the same angle on the equinox dates. It's because we are seeing a reflection. And I demonstrated that. We're looking like through a glass at it. Very easy to explain. And by the way, guys, the globe earth people have this thing where if you can't explain something that doesn't exist, your whole theory is wrong. Guys, ours is no theory. They have no proof. None. Zero. Zip. Nada. None. There is no proof of a ball. Where is it? Where's the proof of any curvature? Where's the proof of any movement? We have scientific experiments show no movement of the Earth. Don't get tripped up, guys. This stuff, looking through all this, is your proof. Look up at the moon. Do you see it change position? When air is constantly going by that's more moist and less moist through the whole night? No, you don't see it variate at all, do you? It's all a lie. And that's much more than you would ever look near the surface of the Earth to find something. You're looking through much more of a density gradient and much more variation in between. You can have inversions. You can have all kind of crap going on here. We use our brain. We always get it right. God bless you guys. Take care.